So this is the sheet that I handed out on Friday. Notes about Newton's laws with friction. You can see here at the top, we have F net equals ma. If you know the net force, that's equal to the mass times the acceleration. This is the weight. The force of gravity is the weight. It's equal to m times g, the mass times 9.81 meters per second squared. And the force of friction is equal to mu, that's the coefficient of friction. Remember, it's a percentage, it's a decimal, but it's actually a percentage, multiplied by the normal force. The normal force is the reactive force of the surface pushing back against pressure put on it. When an object is just sitting, you can see here normal force only equals weight if objects are just sitting on a flat surface. But if they're accelerating or being pushed or pulled up or down, that changes the amount of pressure on the surface and the reactive force of the surface, which is the normal force. It changes. But the force of friction is always the coefficient of friction between that surface and object and the normal force, whatever that happens to be. So these are the kind of like the foundational ideas for these kinds of problems. So I did this in class, but I'm going to go through all of this again because it was last period on a Friday, and maybe some of this stuff was missed. The here the object is being partially lifted. Just checking to make sure that the recording was turned on. And so here you can see it's being partially lifted, so a little bit of weight is being taken off the object. The acceleration is 0. That means that your F net is 0. It means when you do your free body diagram that the upward forces, in this case we have a normal force from the surface, we have a 45 Newton lifting force. Maybe that's a person pulling on it or whatever. It doesn't make any difference, but there's some kind of lifting force. And acting downwards, we have the force of gravity, which is mg. The force of gravity is always going to be acting downwards. Well, in this case, because the acceleration is 0 and the F net is 0, we can make the assumption that the normal force and the 45 Newton lifting force must equal the mg. So here you have your up forces, here you have your down forces, and they have to be equal to each other. So the normal force, and I don't know if you remember me telling you that when you see F with the subscript n, it means normal force. It never means F net. Unfortunately, like the normal force and the net force, they have the same initial letter, but whenever we're talking about F net, it will always be spelled out net. If it's normal force, it'll just have the n there. And unfortunately, that's the way that things are in physics. I didn't make this up. I'm telling you the kind of the conventions that you're going to see in textbooks. So here the normal force will equal the mg minus 45 newtons because the 45 newtons is taking pressure off the surface. It's no longer feeling the full weight of the object, which is 12 times 9.8. It is being relieved by that much. So quick calculation here. If it were just sitting on the surface, we would have 12 times 9.8, and that equals 118 minus 45 newtons, and that comes out to be, to three significant digits, 72.6 newtons. So that's the case where you're taking a little bit of pressure off the surface. In the next example, we have the object is actually being accelerated up. You can think of this as being on the floor in an elevator, and the elevator is in the acceleration phase. It's accelerating upwards, and if you were standing on a weigh scale down here, you would be able to see the weight on the weigh scale. It's actually not the weight, it's the normal force. The apparent weight would increase because you're being accelerated upwards. And the normal force has to exceed the weight of the object in order to accelerate it upwards. Well, in this case, we again go to our free body diagram, circle, mass in the center. Acting upwards, there is only one force, the normal force. There's there's nothing pulling, there's no external object here that's doing anything with this box. But because it's accelerating upwards, the normal force is going to be more than the weight. So here's what we would say. We know now, in this case, the F net is not 0. We can't assume that the up forces and the down forces are equal to each other like we did in the previous example. Here we were allowed to say the up forces and the down forces are equal because we had an acceleration of 0. But because our acceleration is non-zero, we have a net force. There must be more force in one direction than the other. And in this case, it's going to be upwards. So the net force is acting up, the normal force is acting up, the weight is acting down, and that's why I put the normal force here first, and I'm subtracting the weight because these two are in the same direction. F net is always equal to MA. So now, when we rearrange, we're going to get the normal force is going to be equal to MA plus mg. And, sorry, I got a little mistake there. It's MA plus mg. So remember, our normal force has to do two things. It has to accelerate the object, and it has to counteract the weight of the object pressing down on the surface. When we plug in our values, we're going to get 18 times 1.5, which is 27. And then the weight of the object is 18 times 9.81, which is 177. And we get a total normal force of 27 plus 177, 204 newtons. In number 3, we have an object being pushed down, and it's also accelerating downwards. But you know what? Here's the thing, right? The way to start these problems off is with a free body diagram. Now, I've been arguing with, or not arguing, but reinforcing this with every physics class I've ever had. And there's always a lot of resistance out there. Everybody's sitting down like, I don't need to do a free body diagram. Well, I think it's a good idea to do a free body diagram. And guess who's done a lot of physics? Me. And I'm telling you, it works. It might not seem necessary now, but as you get further along and the questions get more complicated, these free body diagrams allow you to focus your attention. It's what the F net equation is based on. So, that's all I can tell you is that I know a lot about physics. I've done a lot of physics, and I'm telling you, these free body diagrams are a good idea. It's not something that I'm making up to create work for you. They're a good idea. So there's 7 kilos. Now, acting upwards, we've got the normal force. Acting downwards, as always, we've got the weight, which is mg. Fg means weight. Force of gravity is mass times acceleration due to gravity. And then also going down, we have this 45 Newton. Somebody's pushing down. Now, because our acceleration is not 0, we know that our F net is not 0. That means we can't let the up forces and the down forces equal each other. We had to do it this way. The F net in this case is going to equal the up forces, Fn, minus the down forces, mg, minus 45. Oops, I don't know what happened there. The F net is MA. Oops, slight technical difficulties. The F net is MA. The M is 7 kilograms. Now, you can see here that I've put the normal force in as positive, and the weight and the 45 I've put in as down. That means I had to put in my acceleration, and I already did it. I had to put that in as negative as well because it's in the downward direction, and I have chosen that as negative up here. I've chosen the downward as negative, so that's going to be Fn minus 7, 9.81 minus 45. And when I rearrange everything, I can leave the Fn over here if I want. I don't like working in this direction, but who cares? So this is going to be 7 times negative 0.75. That's minus 5.25. Plus, this is going to come over and turn into a plus. So we're going to get 7 times 9.81 is 68.7. And then the 45 is going to come over and become a plus. And now our Fn, now don't get freaked out because I flip things around. I just put the Fn on the other side, so minus 5.25 plus 68.7 plus 45 equals 108 newtons. And because it's positive, that tells me that it's up. There you go. So I'm going to take a little break and just let that sink in for a while. And then I'm going to go down to this one here being dragged at an angle. And now, this is the point in the story where you have to know how trig works. So I'm going to stop the video and